Let's observe the physical reality we are attempting to prove. When two distinct colored fluids are subjected to chaotic, accelerating folds, they rapidly mix until they form a single uniform color. In a piecewise expanding dynamical system, this process is called strict exponential mixing, where the system converges to a unique invariant state. To prove this mixing actually occurs, we must translate the physical geometry into a functional analysis problem. We do this by characterizing the eigenvalues of the Lebesgue density transport operator, denoted as P. Looking at this complex plane, our target is the peripheral spectrum. These are the eigenvalues lying exactly on the boundary of the unit circle at radius 1, while the essential spectral radius, the shaded disk inside, remains strictly less than 1. For true exponential mixing, two conditions must be met. First, the essential spectral radius must be strictly less than 1. Second, the boundary of the unit circle can only contain isolated, simple roots of unity. We will track our progress using this ingredient ledger. This table contains the 9 interlocking mathematical properties required to bridge the global bounds of functional analysis with the point-wise topological dynamics of the physical state space. Proving exponential mixing requires abandoning single-discipline methods. We have to forcefully interlock the geometry of the state space with the functional bounds of the operator space. We begin with the first ingredient in our ledger. The operator P is positive, and it preserves Lebesgue mass outright. This mass preservation is guaranteed strictly by the constant slope branch sum definition of our underlying dynamical map, R. This brings us to the second ledger ingredient, achieving quasi-compactness through the Lasota-York inequality. Because R has a uniform constant slope branch structure, it cleanly satisfies the conditions for Lasota-York. This bounded variation forces the essential spectrum of the operator to compress inward. Returning to the complex plane, you can see this compression in action. The shaded inner disk explicitly shrinks, isolating a few discrete points directly on the boundary of the unit circle. The formal implication is precise. Any eigenvalue surviving on the unit circle is strictly an isolated eigenvalue of finite multiplicity. By applying the Lasota-York inequality, we reduce an intractable infinite-dimensional operator problem into a finite discrete set of boundary eigenvalues. Now we analyze those surviving boundary points. Assume there is an eigenfunction u satisfying the equation pu equals lambda u for an eigenvalue precisely on the unit circle. Recall that our system possesses a unique absolutely continuous invariant probability measure, denoted as h. By combining the positivity of P, its mass preservation, and the uniqueness of H, we can place a strict upper bound on the absolute value of the eigenfunction U. The resulting structural constraint reveals that the magnitude of U cannot vary independently. It must be a constant multiple of the invariant density H. Variation in U is purely a phase shift. Highlighting the cocycle relation, we establish the equation U equals lambda times U composed with R. Over the map's orbit, mapping point x to R of x, the eigenfunction picks up the exact phase shift lambda. Because we are dealing with Lebesgue densities, this exact relation holds almost everywhere across the state space. The cocycle relation is the critical translation layer, turning a global functional eigenvalue problem into a local pointwise tracking problem along R's trajectory. Our previous quasi-compactness result restricts the allowed phase shifts. The value lambda must be a root of unity, meaning lambda to the power of q equals 1 for some integer q. Substituting this back into the cocycle relation, we find that U is completely invariant under the qth iterate of the map, RQ. To constrain this further, we introduce our next ledger ingredient. The state space map R possesses topological exactness. This interval diagram demonstrates topological exactness. A tiny subsegment of the state space iteratively stretches, maps, and folds until it entirely covers the full domain X. Because the base map R is exact, any iterate of it, including RQ, is also topologically exact. A standard property of exactness states that any measurable function invariant under an exact map must be constant almost everywhere. Applying this to the q equals 1 case, we prove that U is simply a constant multiple of H. Formally, this establishes geometric simplicity. The dimension of the kernel of P minus the identity is exactly 1. The pointwise topology entirely overrides the eigenfunction's freedom, forcing H to be the sole unique eigenvector at the leading eigenvalue 1. We face one final mathematical hurdle. We must rule out the potential existence of polynomial growth, driven by a Jordan block at the eigenvalue 1. Assume a vector v where P minus iv equals u. Integrating both sides applies mass preservation. Since the integral of PV equals v, the left side becomes 0. But u, our invariant density h, integrates to 1. This creates a contradiction. The mass preservation property outright forbids the formation of Jordan chains, proving the algebraic simplicity of the leading eigenvalue. Look at the completed ledger. Branch sum mass preservation, Losada-York spectral gaps, and state space exactness are now fully interlocked. As a result, the boundary of the complex plane contains only a single solid point, exactly at 1. With the peripheral spectrum strictly constrained to a simple leading eigenvalue, the transport operator mathematically guarantees true, unbounded exponential mixing for the system.